The next topic we'll look at in talking about acids and bases is something called autoionization. If we think about the parts of the word, we can figure out what it means. Auto means self. Ionization means something is going from neutral particles, usually molecules, to ions. So if we take a look at the first reaction where we have two water molecules reacting with each other and we get a hydronium ion and a hydroxide ion, that is autoionization, or water causing itself to form ions. So the K for this reaction is the concentration of hydronium ions times the concentration of hydroxide ions. And when you multiply those two ions together that are products of water ionizing itself, we get an equilibrium constant called Kw, W for water. So Kw is the dissociation constant for water at 25 degrees Celsius. And at that temperature, the concentration of hydrogen ions, or hydronium ions, is equal to the concentration of hydroxide ions. And those concentrations are each equal to 1.0 times 10 to the negative 7 molar. And this can be determined experimentally. Definition of pH is the negative log of the hydrogen ion concentration. So that means you need to remember how to use the log button and the inverse log button on your calculator. So we take the hydrogen ion concentration, we take the log of it, and then we take the negative, because the log of these numbers are going to be negative values. We also have something called pOH. To find the pOH, we're going to take the log of the hydroxide ion concentration, the negative log of the hydroxide ion concentration. And it turns out that something called the pK is the negative log of the K, of the dissociation constant. Kw is the hydronium ion concentration times the hydroxide ion concentration, so that's here, which means that the pK is equal to the pH plus the pOH, and that's equal to 14. What that also means is that Kw for water at 25 degrees is equal to the concentration of the hydronium ions times the concentration of hydroxide ions, so we can just square that. And so Kw at standard or regular conditions is 1.0 times 10 to the negative 14. And if I take the negative log of that, I get pK of 14. Let's take a look at pH of weak acids. Weak acids are ones that don't ionize 100%. So we're going to have some of the molecule present in the solution, as well as some of the hydrogen ions and some of the anions. Hydrogen fluoride is the one we're going to start with. Hydrogen fluoride has a Ka of 7.2 times 10 to the negative 4. So what we're trying to find out is the pH. What's the pH of a 1 molar solution? Hydrogen fluoride is one source of hydrogen ions. It's going to dissociate, but water also dissociates, as we just finished seeing from autoionization. So if we take a look at autoionization, we have hydrogen ions forming and hydroxide ions forming. And we have the Kw for that of 1.0 times 10 to the negative 14. All right, that is a lot smaller than the Ka for hydrogen fluoride. So chances of hydrogen ions contributing to the pH from water dissociating is pretty much next to zero. So if we want to calculate the equilibrium concentration from the Ka, we have an initial concentration of hydrogen fluoride of 1 molar, and we have zero concentration of our ions. Now, this is theoretical, because when I put hydrogen fluoride, when I dissolve it in water, it's going to instantaneously ionize. So this is not an overtime type of activity. This is an instantaneous activity. But it helps us to figure things out if we can break it down and look at it as if it hadn't ionized yet. Since our equilibrium is not achieved yet, we have to look to see which way it shifts. We have no products, so it's going to shift to the right. So we have minus X for hydrogen fluoride, plus X for both hydrogen ion and fluoride ion. So our equilibrium expression is going to be Ka is concentration of hydrogen ions times the concentration of fluoride ions over the concentration of hydrogen fluoride. And now we put in numbers. So we have X squared in the numerator. We have 1 minus X in the denominator. And our Ka we saw before is 7.2 times 10 to the negative 4. So now we do the algebra solve for X. Our K is small, so what does that allow us to do? Hopefully you figured out it allows us to just cancel out this X in the denominator. So that leads us to X squared equals 7.2 times 10 to the negative 4. We end up with X equals 2.7 times 10 to the negative 2 molar. If that's less than 5% of our original concentration, we're in good shape. Well, 5% of our original concentration would be 0.05. This is 0.027. So we're in great shape. Now our hydrogen ion concentration is 2.7 times 10 to the negative 2, so to find pH, we're going to take the negative log of that. So when we take the log of that, we find out that the pH is 1.57. When we talked about characteristics of acids and bases initially, we said that acids have a low pH. Well, one's pretty close to 0, and that's about the lowest you can get, or so we thought, for pHs. pH of 7, remember, is neutral, and pH is above 7, we have a basic solution. Okay, if we take a look at a mixture of acids, we can find the pH from them. Here we're looking to calculate the pH of a solution. We have 1 molar hydrogen cyanide, and there's the Ka, so it's a fairly weak acid, and 5 molar of nitrous acid is not quite as weak. It's 10 to the negative 4 for its K. So looking at these two Kas, hopefully it's clear that the hydrogen ion contributed by hydrogen cyanide is essentially non-existent compared to the hydrogen ion contributed by nitrous acid. So we're going to focus on that for figuring out our pH. So first, probably the thing to do is to write out the equilibrium reaction, dissociation of nitrous acid. So our equilibrium, our Ka expression, is hydrogen ions concentration times nitrite ion concentration over nitrous acid concentration. So our initial concentration is 5 molar, and no hydrogen ion, no nitrite ion. So at equilibrium, we're going to have 5 minus X for nitrous acid, X for hydrogen ion, X for nitrite ion. So now I'm going to put it into my Ka expression and solve for the hydrogen ion concentration. That will allow me then to figure out the pH. So my Ka is 4.0 times 10 to the negative 4, and I have X squared in the numerator, and I have 5 minus X in the denominator. What do I do about the X? I can cancel the X in the denominator. Doing the algebra gives me X equals 4.5 times 10 to the negative 2, or 0.045 molar. Okay, 0.45 compared to 5 molar, definitely less than 5%, so we're in good shape. So now I need to figure out the pH. So pH equals the negative log of 0.045 molar, and I get a pH of 1.35. So just because I have multiple acids in a solution, it doesn't necessarily mean that each acid is going to contribute hydrogen ions to the solution to make it acidic. In this case, hydrogen cyanide is going to pretty much stay pretty close to 100% as hydrogen cyanide molecules as opposed to dissociating. All right, the second part of this, I'm supposed to figure out the cyanide ion concentrations in the solution. Well, hydrogen cyanide is going to dissociate a little bit, and so I need to write out that equilibrium expression. My initial concentration of hydrogen cyanide is 1 molar, and my hydrogen ion concentration from my nitrous acid is 0.045 molar, and I have no cyanide ions initially. At equilibrium, the equilibrium is going to shift to the right because I need to generate some cyanide ions. So I'm going to have 1 minus X for my equilibrium concentration of hydrogen cyanide. I'm going to have 0.045 plus X for hydrogen ion concentration, X for cyanide. So now I'm going to put that into my equilibrium expression, and I take the Ka for hydrogen cyanide, 6.2 times 10 to the negative 10, and that equals hydrogen ion concentration, 0.045 plus X times X for my cyanide ion concentration, all over 1 minus X for my hydrogen cyanide concentration. Now that K is pretty small, so what does that allow me to do with each of the X's? X in the denominator, normally that's the one we get rid of, so we're going to get rid of it again. My X, my plus X in the numerator here can also be eliminated because it is so small compared to 0.045 molar as to be not considered. Now I have 6.2 times 10 to the negative 10 times 1, and that equals 0.045 times X. So that allows me to figure out the value for my X, and what I find out for X is I have 1.4 times 10 to the negative 8 molar. So I started with 1 molar hydrogen cyanide. Hardly any of it is going to be dissociated to form cyanide ions. Most of it's going to stay again as molecular hydrogen cyanide.